All right, next up, we're going to get into the states of matter, more on gases, and then we'll get to liquids and solids. So we're going to look at something called the kinetic molecular theory. So the kinetic molecular theory makes some assumptions about substances and predicts their behavior. Um, it talks about ideal gases, and we'll get to the difference between ideal and real gases in a little bit. Gases consist of particles, which could be molecules or atoms. So if you had a sample, say, of neon gas or a sample of helium, the particles are individual atoms, versus if you had a sample of oxygen gas or carbon dioxide, then that would consist of molecules. So particles can be atoms or molecules depending on what the gas is. Whose volume is much greater than the size of the molecules themselves. So a sample of a gas occupies a rather large volume considering that the particles that make up that sample themselves are really, really, really small. So what this means is that a gas is almost entirely empty space. 99.9% of any sample of a gas is empty space. The other 0.1%, of course, then is the particles themselves. The particles of a gas are in constant, always moving, rapid, they're going fast, as we'll see later on, linear motion if we're talking about an ideal gas. So ideal gases travel in straight line paths. It's not necessarily true for real gases. Letter C, very, very, very important. The average kinetic energy of gas molecules is directly proportional to the absolutes or Kelvin temperature of the gas. So what's very important to understand is the relationship between temperature and molecular motion, temperature and kinetic energy, temperature, I think I said them all, temperature, molecular motion, kinetic energy, molecular motion. All gases, regardless of their molecular mass, have the same average kinetic energy at the same absolute temperature. Now let's think about this for a second. What exactly is the definition of temperature? Go ahead and pause and think about that for a second. Now some of you might think that temperature is a measure of how hot or cold something is. Well, that's a relative term. Temperature is a measure of the average kinetic energies of the particles in an object. And so we have this direct correlation between temperature and kinetic energy. And so if you have two different substances, let's say at the same temperature, then the average kinetic energy of the particles will be the same. Letter D, also very, very, very important. So we'll talk a lot about collisions between gas particles and the walls of their container. So it says collisions of gas particles with themselves, and more importantly, at the walls of their container, are perfectly elastic. An elastic collision is one that does not involve a loss of kinetic energy. If the particles of a gas were involved in inelastic collisions, where each collision resulted in a loss of kinetic energy, kind of like when you bounce or drop, rather not bounce, but drop a basketball or volleyball, let's say, on the ground, that collision involves a loss of kinetic energy. What would happen to the particles if they were involved in inelastic collisions? Well, every collision would cause the kinetic energy of the particles to decrease, and eventually the particles would just stop moving. So inelastic collisions of particles, even though they're colliding all over the place, they change direction. Their kinetic energies don't change, but they just do change direction. All right, so these graphs, next series of graphs, we have the Boltzmann distribution and kinetic energy distribution curve for students in Chem 1 has caused some issues, so make sure you know what this graph is showing. Boltzmann distribution is a graph of the number of particles versus speed. So let's go ahead and set that up. Go ahead and set up these axes, number of particles on the y-axis and the speed or velocity on the x-axis. And so what we would see if we consider a sample of a substance. So look back at the definition of temperature. Temperature is a measure of the average kinetic energy of the particles in an object, implying that different particles have a different amount of kinetic energy. Remember that kinetic energy is calculated as 1/2 mv squared. So kinetic energy is related to velocity or speed. And so if the particles of an object or a substance have different amounts of kinetic energy, if we're talking about the same substance, they must have different velocities. And so what this graph shows is the distribution of velocities of the particles of a substance at some temperature. And so we get something, not really bell curve, but something like this. And it doesn't necessarily have to hit zero, just kind of hit zero there. So what we're going to show is the effect of temperature on speed. So let's say we have some substance at 20 degrees Celsius. First of all, again, a point right here, let's say, tells us that there are very few particles that have, or are moving rather, at a very low speed. Over here, let's say, again, we have very few particles that are moving at a high speed. And then here, we have a lot of particles moving at some intermediate speed. And then we have everything in between. So again, all the particles of a substance are moving at different speeds. This curve or distribution shows all of those different speeds. Now, something important to note as well, for those of you that in calculus may know how to do this, if we were to calculate the area under the curve, so this entire surface, this area here, all the way under the curve, what would that tell us? Go ahead and pause and think about that. If we were to calculate the area under the curve, that would represent the total number of particles. So that's important for this and the next graph that we'll show. Let's do this. Let's show on this same graph the effect of temperature on speed. So let's take this same substance and heat it up to, say, 50 degrees Celsius. Well, if you increase the temperature, this is going to cause an increase in the average kinetic energy of the particles. And if the average kinetic energy increases, then the average velocity will also increase. So let's draw a second curve. What does this second curve for this substance at a higher temperature look like compared to this curve? Again, we want to show that at a higher temperature, there are a greater number of particles that have a higher velocity. And so that curve is going to be shifted over to the right. So let's label that as 50 degrees Celsius. Notice that this curve is shorter than the blue one, but it's wider. Hopefully I tried to show that the area under both curves is the same, again, because we're not talking about a difference in number of particles, same number of particles, same substance. So at a higher temperature, on average, the particles are moving faster. At a lower temperature, on average, the particles are moving slower. Well, what if we did like negative 10 degrees Celsius? What would that curve look like relative to the blue and red curves? Well, at negative 10 degrees Celsius, lower temperature, on average, the particles would be moving slower. And so we'd have a higher distribution of particles that had low speeds, and so we'd get a curve that shifted over to the left. So there it is again, the area under the curves is equal because we're talking about the same substance and the same amount of that substance. And again, very, very important, the average speed of the particles is higher, in the higher temperature rather, in the higher temperature sample is greater than the lower temperature sample. So again, temperature, molecular motion. Make sure you understand the relationship. All right, go ahead and turn to page 428 in the textbook. I think I skipped something. Let's go back. All right, sorry about that. Let's go to number 2 first, and then we'll go to the textbook. All right, this time we're going to show different gases at the same temperature. So again, let's set up our axes. We're going to draw 2 graphs here, by the way. 2 graphs, 2 different graphs. So puts this first one over to the left a little bit, and then we'll talk about the second graph. So let's set up our axes. Whoops, I do not want to use that color. So let's try again. Same axes, speed on the x-axis, number of particles on the y-axis. All right, so let's show two different substances. So let's just make this one here. Let's say this represents the distribution of the velocities of oxygen molecules. So again, the difference here with these graphs is we're looking at not the same substance, different temperatures, different substances, same temperature. Okay, so let's show helium on this graph as well. So how do helium atoms compare to oxygen molecules? Well, helium atoms are less massive, they're lighter than oxygen molecules. So going back to our equation for kinetic energy, mass times velocity is equal to kinetic energy. So that tells us that mass and velocity are inversely related. So for the helium, since it is a lighter particle, at the same temperature as the oxygen, the lighter particles will move faster. So how do we show this on this graph? That's the helium atoms, and let's put in a temperature here too. Let's say that both of these gases are at 20 degrees Celsius. Let's take some helium at 20 degrees Celsius. Same temperature, same average kinetic energy, different masses, therefore different velocities. So helium at 20 degrees Celsius, on average, the atoms, the particles are moving faster than the oxygen molecules. Same kinetic energy, because they're at the same temperature, different velocities. Let's do this. Let's over here draw what's called a kinetic energy distribution curve, which shows the distribution of kinetic energies of the particles. So same y-axis, number of particles. Let's say this is a curve for oxygen at 20 degrees Celsius. Go ahead and pause the video, and on that graph, draw the curve for helium at 20 degrees Celsius. Go ahead and pause now. Is that what you got? So again, same temperature, so that means the average kinetic energies are the same. So don't confuse these two graphs, kinetic energy distribution curve with Boltzmann distribution. Boltzmann distribution shows speed. So as we've already talked about, lighter particles move with greater average speeds in order to achieve the same kinetic energy. So how about this then? Lighter gases move faster than heavier gases when at the same temperature. That's what that first graph is showing there. Helium atoms 4 AMU, oxygen molecules 32 AMU. The helium atoms, because they are lighter, will have a higher velocity than the oxygen molecules. And I believe this is a mistake in your notes. So instead of looking at figures 1210 and to 1212 and 428 and 429, let's look at page 427, figures 12.8 and 12.9. So showing the same thing, we got number of particles versus speed. Whoops. And just showing the same stuff that we had already talked about in the notes. All right, so let's do this. Let's see how to calculate average velocity or molecular speeds, as it says here. So there's an equation on your equation sheet for something called root mean squared velocity. Don't worry about what that means. It's just how we can calculate the velocity of some particle. So I'm not sure why it's not V, but it's U, so RMS. So find this equation. Square root 3RT over M. So R is the ideal gas constant. Now be careful. We're trying to calculate velocity in meters per second, right? V is in meters per second. Well, we have ideal gas constant. We have T, which is the, as we'll see in a second, the temperature, and M. Here, let's fill this out. So T is the temperature in Kelvin. Big M here is not molarity. As we said, the velocity of a particle is affected by its molar mass. Be careful though. In this equation, the molar mass is in kilograms per mole. So how in the heck are we going to get to meters per second with all this? Well, we're going to use this value for R, 8.314 joules, there's our mole, per mole Kelvin. So we have our moles there, that's going to cancel with moles there. We need kilograms to cancel. Again, we need to be left with meters per second. So let's go back to this. A joule is a kilogram meter squared. Oh, there's meters per second squared. There's seconds. So that's why we have a square root. We have meters squared per second squared. So everything's going to cancel. Moles will cancel. Kilograms will cancel. Kelvin will cancel. We're left with meters squared per second squared, and that's why we'll take the square root of that. All right, turn to page 431. Let's take a look at the example. Read along. It says calculate the root mean square speed of hydrogen molecules in meters per second at 20 degrees Celsius. So we're just plugging some values in. So take a look at the bottom of the solution there. 3 times R. Notice R is not in joules per mole Kelvin, but the book has converted to kilogram meter squared per mole Kelvin seconds, so that the units are taken care of. We're substituting for joules. Temperature 293 Kelvin divided by the molar mass, which is 2.02-ish grams per mole. We got to convert that grams to kilograms. And then we take the square root of everything. Everything cancels except for our meters per second, and we get 1.90 times 10 to the third meters per second. That's pretty fast. 4,250 miles per hour. Remember, hydrogen molecules are really light, and so they're going to move, as we can see there, really fast. You'll get a chance to do some more examples like this later. All right, changing gears, sort of. Diffusion and effusion. Be careful, they are different. There's some properties that are similar. Diffusion is the movement of movement of a gas from where there's a lot to where there's not a lot. Here it says the mixing of molecules of 2 or more gases due to their molecular motions. Take a look on page 432. Top of the page, you have 2 different gases, oxygen and nitrogen, in separate containers. If you were to open the valve, it says stopcock there, or valve. Open the valve, the oxygens are going to move from left to right. Nitrogen molecules are going to move from right to left until they're evenly dispersed between those 2 bulbs. That is diffusion. Effusion is the movement of a gas through tiny openings into a container of lower pressure. So think about this. Think about a helium balloon. When you purchase helium balloons, they're nice and floaty because they have lots of helium inside, and then a day or 2 later, the balloons sink. Well, why do they sink? It's because the helium inside those balloons leaks out. There's tiny pores in the walls of the latex that the balloon is made of, and those tiny helium atoms are able to basically leak out from the balloon. We can see an example of this in figure 12.4 on that same page that you're on, and it shows gases effusing, leaving their container. That silvery mylar balloon, the pores in mylar are much smaller than the pores in latex balloons, so those mylar balloons stay floating a lot longer. All right, so let's do this. I'm going to derive Graham's law of diffusion, or Graham's law of effusion, same thing. And it's based on this. You have, let's say you have 2 different gases at the same temperature. So I'm going to start the derivation up here. So the kinetic energy of gas 1 is the same as the kinetic energy of gas 2. We can substitute for kinetic energy. So 1/2 m1 v1 squared equals 1/2 m2 v2 squared. So their kinetic energies are equal, and so we get this relationship. Well, let's get rid of these 1/2s, and so we end up with m1 v1 squared equals m2 v2 squared. Let's rearrange so that we have The velocities, both on, let's do them on the left side. So let's divide both sides by V2. And let's move the masses over to the right side. So let's divide both sides by M1. So V2 cancels there, M1 cancels here. And so we get, whoops, V2 squared, that should be. So we have V1 squared over V2 squared equals M2 over M1. Last step, let's square root both sides. And so what do we end up with? We end up with Graham's law of diffusion or Graham's law of effusion. So we have, I'm going to write it one of two ways. I'm going to write it this way. V2, whoops, it's not V2. V1 over V2 is equal to square root. Now be careful, what's on top? We have M2 over M1. Sometimes it's written this way. The rates of effusion or diffusion, which is relative to the velocity of the particles, over the rates of effusion or diffusion of gas 2 is equal to the square root of the ratio of mass of the gas 2 to mass of gas 1. So be careful with how those fit into the equation. Now, a couple things to keep in mind. Molecular motion is dependent on two things. One, temperature. Two, velocity. So if you have two different gases at the same temperature, they're going to have different velocities because they have different masses. Likewise, if you increase the temperature, the velocities of both gases would increase. When velocities increase, so does diffusion, so does effusion. All right, so that is Graham's law of whichever you want to call it, diffusion or effusion. Let's take a look at an example. Suppose that the velocity of a hydrogen molecule at some temperature is 1.84 times 10 to the third meters per second, and the velocity of some unknown gas is 311 meters per second. Now, this should tell you something. What does this mean about the mass of the unknown gas compared to hydrogen? Well, notice that the velocity of the unknown gas is less than the velocity of the hydrogen. So what I want you to do is use Graham's law of diffusion to determine the molar mass of this unknown gas. And once you get the molar mass, see if you can identify what it is. So go ahead and work on that. Pause the video now, please. So it doesn't matter which you decide to make gas 1 and gas 2. I wanted to solve for the number on top here. So I made the unknown gas 2. Work just as well the other way, but be careful if you're solving for M1. When you divide these two numbers and square both sides, you're going to get the inverse of the answer. And so you need to make that adjustment. So you end up with 70.7 grams per mole. So which gas has a molar mass of about 71 grams per mole? Looks like this could be chlorine gas, which is about 71 exactly, 70.9 grams per mole for chlorine. I want to continue with this lesson, but I'm going to stop the video here. On the second video for this lesson, we'll show the difference between real gases and ideal gases, so make sure to tune into that video as well. Thanks for watching.